this nice workshop and the invitation. So I take the opportunity today to speak about Subgame Perfect Equilibria. And so I will do it with some, and present mostly new algorithmic ideas to solve problems related to Subgame Perfect Equilibria. So I will summarize works that I did with Marie van den Bogart from the University Gustave Eiffel in Paris, and Leonard Brice, who is a PhD student in my team in Brussels. Okay, so the objective of the talk is I will try to convince you that somehow Subgame Perfect Equilibrium are the kind of equilibrium that we should look at when we are considering game played on graph, because they are better suited, I will claim, that Nash equilibrium. I mean, it's not a claim that it's not my claim. It's a claim that is long ago around for games played sequentially. So we will see why. And then, so this SPE will be to model rational agents, rational player in games. Okay, and as I said, so I will mainly present you algorithmic ideas, and I will summarize results that we have for parity and mean pair of games, and most of the examples that I will present will be for mean pair of games. Okay, so because they are a bit more challenging. Okay, so what is the setting? So we already had several talks about games, so it will be quite similar. So maybe a bit different from the games that were presented by Marta that were concurrent games. Here I will go for the simpler setting of turn-based game. Okay, so I have a finite graph with vertices that are partitioned according to the player. So in this example, so I have three players, so the circle player, the square player, and the triangle player. And so so we play on this game as usual. So we have a token that will move along the edges of the graph, and so it will create an infinite path in this graph, and this will be called the outcome of the interaction of the players. And so I will also consider so games where the states are annotated either with vector of color, so that will define for each player, so each dimension of the vector will be assigned to one player, and so it will define a winning objective for the player, right? And so I will also consider vectors of rewards that will basically assign payoff to the player. Okay, so one dimension per player. And so for the parity condition, as usual, so the player will, so the winning condition for player I will look at the dimension I of the vectors, and so we will look at the colors for that dimension that repeat infinitely many times, and if the minimal color among those is even, then it will be declared as winning for player I. For the mean payoff, so we simply compute the running sum of the dimension assigned to the player and take the mean, and so we are interested by the limit of this running mean. Okay, and so roughly, so by rationality, here I mean that player want, in some sense, to maximize their own payoff in this setting, right? And so we will see what it really means formally later on. Okay, so that's for the setting. And then, so I will manipulate notions like strategies, profiles of strategies along the talk. So let's make it clear what are those. So a player, he will play according to a strategy. The strategy is simply a function that, given an history that ends up in a vertex that belongs to the player, choose an edge that is leaving that vertex. Okay, so you can see this also as the unfolding of the game graph, and then so in this infinite tree, each node that ends in a state that belongs to the player, you should do a choice, right? And this choice can depend. So even if some states are repeating, this choice can depend on the full history that we have seen so far. And when I speak about a profile of strategy, simply one strategy for each of the n players, right? And so when you do that, so if you fix a strategy for each of the players, so what you get at the end is the outcome associated to the profile of strategy. Okay, so is it clear? Okay, so now why do we want to model rational agents? So it's because, so when you have, say, an arena like I've shown that is modeling, say, a protocol that is used by agents that are rational, so they have their own objectives, then you can ask questions like, so what happens if agents resolve non-determinism that is left in the protocol rationally? So is it the case that some good property will emerge for sure? Okay, so do all rational executions satisfy some specification? So that's the kind of questions that we would like to answer. Is there a rational behavior of the participant in which all the participants has some least gain, but at least they gain at least C, and so on. Then you can ask also more basic questions like, is there at least one rational execution of the protocol? Or are all the possible execution of the protocol rational? Okay, so we are aiming to answer those questions with algorithm. Okay, and so to model rationality, if you look in the literature, so you will find several so-called solution concepts that are meant to make precise what it means to be rational. And so if you think about simple setting like one-player games and maybe so shortest path, then so you expect, so if you fix A and B, say in a weighted graph, you expect that a rational player will try to choose one path that minimizes the total sum of weight along the edges, right? There can be several of them, but at least this notion will somehow allow you to predict how should the agent behave if he is rational. So then, I mean, this is the simplest settings, and we use that all the time. But now, if you have even one player, but with several objectives, then it becomes more tricky to predict how a player will play. But for example, you can assume that he may want to play a Pareto optimal path in that case. Okay, and now if you go to the n player setting, then you have a large number of different solution concepts that can be used. So there is this, I mean, the famous Nash equilibria. So what I will speak more today about is the subgame perfect equilibria that are strengthening of Nash equilibria. But you have also other notions like admissible strategies or dominant strategy and so on. Okay, so that's the broad picture. And so today we will concentrate on SPE. Okay, so I will first, to define SPE, I should first define what is a Nash equilibria. So a Nash equilibrium is a profile of strategy. So it's one strategy per player in the game graph, such that, so intuitively, no player has an incentive to change his strategy if the other one stick to their strategy. Okay, so this translates mathematically as follows. So you want for all the players in your game graph the following to be true. So for any strategy that would replace their strategy in the profile, the outcome that they will get, so it's the outcome for player I, so the value of the outcome for player I should be less or equal to the value of what get player I with the original strategy in the profile. Okay, and so if this is verified for all the strategies, we say that we have a Nash equilibrium. Okay, and so this is something that you may expect to see emerging in the behavior of agents that are rational. Okay, and so let's take some examples. So here I have a simple game that I duplicated here, and so we have two players, and so basically there are two different strategies for the square player, right? And there are 4 different strategies for the circle player, right? So we choose one of the two edge in each of the of its nodes. And so if we look at this graph, so here I have given payoff to both players at the leaves, and so you can think of this as a mean payoff where we will cycle here and they will receive exactly this payoff, right? And so I claim that the two strategies, the two profile strategies that I've highlighted here are Nash equilibria. So let's take the first one. So here you see that we go there and then we will go there. So the outcome of this Nash equilibria is 5 and 10. And you see that if the square player would change and deviate from this, he would get 2 instead of 10. So no incentive to do that. So this is okay for the square player. And so now the round player has no incentive to change because here he gets 5. And if he would change, he would get 1. And here, if he changes, it does not matter because anyway, we will not go there. Okay, so this means that this is a Nash equilibrium. And then we can do the exercise on the other side and see that it's also a Nash equilibrium, right? Because you see that here the square player gets 2, right? And if he would move to this, he would get 1. So no incentive to do that. Then here it's not important because we will not reach this under the strategy of the square player. So we should look here, and here there is no incentive to change because the circle player gets 10 and there he gets 1. Okay? But if we look at the second Nash equilibrium, I claim that it's not a natural one. Why? It's because if you look at this node here, you see that the circle player now is able to choose exactly the outcome that he will get. And you see that he chooses 1 instead of 5. So in this sub-game here, he is not rational. Okay, and so this is well known, and this is called a non-credible threat, and on which some Nash equilibria are relying to exist. Okay, and so we would like to avoid this kind of situation where in a sub-game, to ensure the existence of a Nash equilibria, some players are playing irrationally, right? Because in reality, if we consider this game and then the square player decide to go there, then it's not reasonable to believe that the circle player will indeed play this, right? So he will have an incentive to deviate. Okay, so that's not a Nash equilibria in this subgame. Okay, and subgame perfection is exactly removing this. So it is asking that for all possible histories in the game, and so this is the unfolding of the game. So if we take any histories in the subgame, we should observe a Nash equilibrium also for the profile to be a subgame perfect Nash equilibrium. Okay, and in my example here, this is not the case for this subgame. Okay, so now what's the formal definition? So it's very similar to Nash equilibria with the difference, the important difference here that we are quantifying over every histories, and we want that for every histories, what we have is a Nash equilibrium. Okay, so no incentive to deviate in any of the subgames. Okay, so that's the thing. So the problem is that when you adopt this definition, then algorithmically things are more complicated because you have added this universal quantification here, and so we will see how we can provide algorithm for this game. Okay. Okay, and as I said, I mean, we can verify that this indeed is not an SPE, while this one is an SPE. Okay, so what is the objective of my talk is to provide algorithm that will be able to construct an effective representation of this set that I called old SPE. So it's the set of outcomes in the game graph that are supported by SPE, right? So you can do you can also define the outcomes that are supported by Nash equilibria, and so it's all the outcomes that are observed when we play a Nash equilibria. Okay, so that's, and then now if you think about the definition of subgame perfect, yes. No, the outcome, yeah, I mean, outcome is the what we observe, the play that will be the outcome of the profiler strategy, and the reward is denoted by this mu function. Okay. I mean, yeah. So it's, yeah, it could be maybe better vocabulary, but I will call outcome the play that results from the execution of the profile. Okay, so if we look at these two sets, they are related like that, right? So all the SPE are Nash equilibria, so they are inside, I mean, this set is inside this set, but all those outcomes that are not supported by an SPE, they are supported by Nash equilibria, where you use the non-credible threats to ensure the existence of the Nash equilibria. Okay? And so we want to compute an effective representation of those sets. Why? It's because it will allow us to answer questions like, does there exist an SPE? Simply by checking. So if you have, say, an automaton that recognizes the set of outcomes that are supported by an SPE, then you will check emptiness of this automaton. And so you will have an algorithm for the existent problem. So we will see that for parity games, this set is always non-empty. So this will be trivial. But for mean pair of games, this is not the case. So this question makes sense also. So the existence problem. And then you have so what we call rational verification. So you have this set of outcomes that are supported by SPE, and you may ask, does there exist at least one which would enforce some specification, right? And then if it is the case, maybe you want then to instruct the players in the game to behave like the SPE that you have identified. Then you can ask the dual question, is it the case that for all the SPE in the game, or all the outcomes that are supported by SPE, is it the case that some specification is satisfied? And then you can make also a nice link with the notion of cooperative rational synthesis defined by Orna, where it asks for the existence of an SPE where one designated player is winning his own objective. Okay, and so let's try to see how to handle those SPE algorithmically. So as I said, my main objective now is to define an algorithm that will construct an automata. And so we will see which kind of automata we need to recognize all the outcomes that are supported by SPE. Okay, and so if you look at the literature, as I said, I mean, this notion of SPE, in fact, was proposed in the 70s or even maybe in the 60s by Kuhn. So exactly for the same reason that I mentioned, so to avoid, I mean, those strange Nash equilibria that are not really intuitive on sequential games. And so basically, this notion of SPE was first defined on finite trees. And for finite trees, we have very elegant algorithms that are based on backward induction. So if you want to compute the SPEs of this game, so what you will do is you will ask yourself, so what are the optimal actions that the player here close to the leaves can play? Okay, and so we see here that he should go to the left, right, because he can get 5. And so now you can forget about the subtree and then label this node with 5, 10, and then you go up the tree like that. And then you will get a value here, and then basically all the paths in the tree that have this value are supported by an SPE. Does it make sense? Okay, so this is easy. But we are, and then if you apply this, you will indeed identify this as an SPE, and this one as not being an Nash equilibrium, but not an SPE. But so we are working on infinite duration games, so this idea of using backward induction do not generalize easily, and so we will need something else. And so what we will do instead, so we will start by a characterization of Nash equilibria first, and then we will see how to, I mean, somehow extend these characterizations to be able to obtain a characterization for SPE. Okay. Okay, so how do you, so now I would like to characterize what are the outcomes that are supported by a Nash equilibrium in an arena. Okay, and so I claim that I can do the following reasoning. So, yes. So the characterization will be general, and then I will say how it goes for parity and for mean pair. But I claim that, so if I take an infinite path in the arena, it will be supported by a Nash equilibrium if for every node along this path, okay, it is not possible to deviate from the path and gain something for the player that owns the node. Okay, so I will do that for all of them. But so you know, if you look at this vertex here, so it belongs to player I. So I claim that, so this is supported by a Nash equilibrium if deviating will not be beneficial to the player I. And for that, I will verify that what I get for player I along this path, so let's say that it's the value C, so this C is larger or equal to the worst case value that he can ensure from this vertex V. Okay, so here you may recognize the definition of the worst case value. So you quantify universally over all the strategies of the adversary and existentially over the strategy of player I, and you will find the adversarial value for player I, and this value should be less or equal than the value C given along the outcome. Okay, and so it means that if this is the case, there is no incentive for player I to deviate here because the other ones can now collide and then make sure that he gets less than C. And this will be for all the path, all the vertices along the path. Okay, and so you can see this dually, and so it may be a bit more intuitive. So a path will not be supported by an SPE if it gives to player I a value C, and by deviating, player I is a winning strategy that allow him to get strictly more than C. And these two, by determinant C, are equivalent. Yes.
So, supremum of sigma I, you mean you quantify over sigma I?
Yes, right? So it's all the strategies of the other player. Yes.
But this is fixed. Sigma minus I should be fixed, right? You don't. The other player are not changing the strategy.
Yes. Oh no. I mean, so I'm not. Here I'm asking, does there exist a Nash equilibrium for this path? Okay, and so I can cook a Nash equilibrium for that path, and if I am able to do it, then I will.
Outcome. Yes. Yeah.
Okay. And so this is how I can characterize Nash equilibrium. So you need to remember that computing the worst case value is the way to characterize a Nash equilibrium. And so it's because whenever you take a play, it will be supported by a Nash equilibrium if the value given to the play to player I, for all I, is larger or equal than the worst case value that he can get along this play. Okay? Yes.
Sorry, maybe it's a stupid question. The V, so you look for the value, the I is one of the players, and yes. The V is a node. But
V is a vertex, yes, a node, yes.
So the V is the VJ.
VJ?
Well, I'm in your formula.
Yeah, so value. I take all the position in the play. Okay, and then I look at who is the owner of the position. So it's player I, and it has to be the case that the value of the play for player I is larger or equal than the value that he can force on itself from this vertex.
I mean the next line. I see the V on the left, but not on the right.
Not on the right, yeah. So it should be the outcome starting from V.
Starting from V. Okay,
yes,
good.
Thank you. Yes. Indeed. So here it should be mentioned that it's the outcome starting from that vertex V. Thank you. Yes.
No, very quick question. How do you show that this path is realizable by some strategy, some Nash equilibrium? Because this is supporting, no?
Yeah, I mean, so basically, if I have such a path that has this property, what I will instruct players to play along this path is exactly the edges that are appearing in the path, right? And then for any deviation, I will instruct the player that do not deviate, so to play against the player that has deviated, such that they inflict him a value which is the worst case value. Yes. Okay, so whenever I have a path of that form, I can indeed construct a Nash equilibrium. Yes.
I think I'm asking Igor question. You're never saying here that the path is the outcome of the strategy. Something seems to be funny here.
No, the profile are quantified existentially. So I have a path,
Yeah.
and the question I am asking, does there exist a profile which is a Nash equilibria, and which, when the player plays this profile, we observe
So, but
this
if you go back,
play.
go to the next
Yes.
slide,
Okay.
the play row. Where do you say that row is the outcome
I mean,
of that strategy?
I just here they are quantified existentially.
Is supported
So by one.
No, but if I look, it's supported by if, and for the rest of the sentence, I don't see where you're talking about where you say that row is the outcome of that Nash equilibrium.
No, I claim that if this is true,
Yeah.
if this is true, then I can construct a Nash equilibria that will, as an outcome, this path. Okay, and so the construction is easy. So I take this outcome that has this nice property, right? And so I claim that now I will tell you how the player should play. So along the path, they should play as the path instruct. Okay, and so this will. So if they play along,
but yes. It still seems to me the way I would have gone it. First, characterize the Nash equilibria. You have a set of Nash equilibria, and then for each Nash equilibria, there is an outcome.
Yes.
The problem by starting with the path first, it works for Nash equilibria. It's not going to work for SPE.
We'll see. I mean, that's the magic after, right? But okay, but you agree that here I can take this path and then cook a Nash equilibria from that path if these properties are verified. And this is I need this property. If this property is not verified, so I am in that situation, and the path cannot be supported by a Nash equilibria. Okay, so it's an exact characterization of the path that are supported by Nash equilibria. Okay, and so let's. So at some point, so what I will do, basically, I will now consider only prefix independent objective because it will simplify matters. But we can always go to this case with some classical transformation. But so what I will do now, maybe I should take an example. So I will compute this worst case value. Okay, so here I have a simple min pair of game with two players, circle and square, and I will compute for each state what is the worst case value that the owner of the state can enforce, right? So let's try to see why these are those values. So in this state, okay, let's start with this one, which is trivial. So here the value that the circle player gets, so it's the first dimension, so it's 1, right? So the worst case value is 1. There is no other possibilities. In this one, so he can maybe go there, but then he take a risk, right? Because he gets 0, the adversary or the square player could go back here, then he would go there. So it's not a wise idea. So to get more than 0, he can go there for sure, and then get 1 again. So that the worst case value is 1. I mean, you can convince yourself that that's the case. So B here, should it goes there, so he can maybe hope to get 3, but then he runs the risk that this guy will go there. Right? So the only way for ensuring a good worst case value is to go right. And there he will get 2. So the worst case value for him is 2. And this is 2 also here, trivially. Okay, and so I claim now that any path that you would construct on this arena that is consistent with the worst case value in the sense that it gives to the player the value that we have seen along the path, at least the value that we have seen on the path would be a Nash equilibria. And so in this case, the set of, so I call lambda this function that associate the worst case value to the states. So the set of paths that are lambda consistent are exactly those. So let's take a look. So I claim that going from A to C and then stay there forever is a Nash equilibria, right? Because again, so if player 1 deviates and goes there, he runs the risk to get 0. So he will not do that. Okay, and so he cannot hope better than 1 on his own, right? So that's why this is a Nash equilibria. Then another Nash equilibria is to go that way here and cycle here. So you can cycle a bit on this these edges here, but at some point you need to go there. Why is it the case? So if you take, for example, the outcome that would be AB forever, then it would give 0 to player circle, and then he would have an incentive to go there. Okay, so this is exactly all the paths that are supported by a Nash equilibrium. Okay, and so this is a result that has been obtained by a colleague of mine in Mons, Thomas Brier, 10 years ago. Okay, so that's the starting point. But so basically from that lambda labeling function, so you can, in the case of min payoff, obtain, so you can somehow see this lambda function as defining a multi mean payoff automaton. So this class of automata that has been studied by Rajiv Alur also 10 years ago. And so it defines languages that are not omega regular, but emptiness is decidable. And so, it could be used to answer all the questions that I am after. Okay. So if you take a parity condition for each of the player, what you get at the end with this labeling function is a conjunction of parity objective, if you like. So it's a street automaton. Okay, and so you have a street automaton that characterizes all the Nash equilibria that are supported, all the outcomes that are supported by a Nash equilibrium. Okay, but so now I want to go to the subgame perfect equilibrium, right? And so how do I do that? So what I will do is I will extend the notion of worst case value relative to rationality. So I would like now to compute a worst case value, but making assumption about the rationality of the adversary. They will not able to play anymore as they want, but they will need to play in a rational way. But this will be done incrementally. And so intuitively, so if you compute this worst case value there, in my example, so you may now ask yourself, okay, so I can get 1, right? But now if I go on the right, maybe so the adversary now will not inflict me 0 because maybe it's not rational anymore for him, right? So it's a question like that I would like to answer. And so if we look, so intuitively, so given the worst case value that I have computed, I would like to know if for a player I, he has a strategy to improve the value that she can obtain from the vertex V if the other players are not willing to give up their worst case value. Okay, so if they are not willing to give up their worst case value, so can I improve mine? Okay, and so this will be basically compute a new notion of worst case, which is relative to the rationality or the value that we have already computed for now. Okay, and so what we will do is we will take this this function that assign values to the vertices in the graph. So here the vertices should appear. But so we will take this value and then ask, given the vertex V, is it the case now that I can do better? And so you see here I will alter this quantification over the strategies of the adversaries and now limit those to behaviors that will not imply that they will get less than what their worst case value allow them to get, right? And so this is, and so if you think about my example in the beginning, so here, so I will not allow anymore this edge to be possible because from there the worst case value that the player circle can do is 5, and so he cannot take this anymore. And so this will suppress this non-credible threat in this example already from the first iteration. Okay, but so let's try to understand now what happens on an example. Yes.
Can you go back to this example? Yeah.
Yes, this one.
So
yes.
on the right-hand side.
Yes.
So in case, well, this would be a larger tree, and the green player, the circle player, could avoid that this edge will be visited, that this vertex. So if the tree is larger.
No, but the question that I'm asking is, no, I reach this node, right? So
yeah,
what would be a rational? So you see that, so basically with my annotation, this node would be annotated with 5, right? Because the worst case value that he can
That's
do
what I
is
understood.
5. Yes.
So now I suppose that the tree is larger. So not just the red one, the box player who can decide to go left or right.
Yes.
So if it would also be the green player, instead of a box at the root, we have the circle player.
Yes.
And if the circle player could avoid to go to the left, would it then be okay? Because then
so yeah, if he goes there, he would go there, right? So if this would be a circle, he would go there because he can get 10, which is better than 5, that's for sure. But now, if we start the game here, the story will be different. So I mean, so it's not because there is a good path there that you are allowed to play irrationally here. So you need to play also rationally from here. So it means that in any case, if we are interested in SPE, the only rational choice for the circle player here is to play this edge. Okay. Okay, so let's try maybe to understand what happens on one example. Yes.
It is clear that you cannot get exactly this value, so it's a limit value. So it may be that there are many things that can happen. So
yeah, but
there may be profile that doesn't get this value, but actually it may be that player I gets more than this value, no? Always, because it's also the limit on the other side.
So, I mean, the inf, I mean, we can replace it with so it's a inf here, right? So it's not, yes. So we can replace it by a min. I mean, in the particular case of min, payoff, and parity, you can safely replace those by min.
So a concrete question is there a profile that gets this value exactly?
Yes.
Always?
Yes.
Okay.
I mean, for min, payoff, and parity, yes. Okay, so, but no, I mean, before we were basically so reasoning on the worst case value. Here it's more complicated. So what I will do is define a notion that I call abstract game that will allow me to compute the value of the negotiation function. So the idea is the following. So if you start in a vertex V that belongs to player I, so prover will try to prove that you cannot improve your value from that vertex, right? So the question is, so when we have this worst case value, is can we improve those worst case value if you are not facing adversaries that are completely adversarial when we deviate, but that should behave rationally, right? And so the question is, given this, can I improve the value that is labeling the state? And so, so I will use a game for that. And so this game will be played by a prover that want to prove that you cannot improve on the value that you have for the moment, and challenger that will represent player I, and he will try to improve on that value. Okay, so prover will represent all the other players, and challenger will represent player I. Okay, and so the idea is the following. So we will make sure that prover can only propose moves that are rational. Okay, and so for that, what we will impose is that from V, the play will be, the game will be played as follows. So prover will give not only one edge, but it will give an entire execution. And the constraint is that this execution should be lambda consistent. Okay, so we have seen that so proposing something which is not lambda consistent does not make sense, because otherwise there will be deviation, right? And so you propose this lambda consistent play, and then now two things can happen. So maybe challenger say, okay, I agree with what you propose me. I have no incentive as a representative of player I to deviate, and I accept your lambda consistent play. And in that case, the value of the negotiation function for V will be the value starting from V for player I of this proposal done by player prover. Okay, and so another situation could be the case that what you propose to challenger is not good, in the sense that he say, okay, I can improve on what you propose me, I can deviate and go to, so in that state that belongs to player I can deviate and go to that new state. Okay, and then in that case, the game continue, and prover will propose a new lambda consistent play. And so you see here, for example, he cannot play completely adversarially. He needs again to consider a lambda consistent play and be consistent with the worst case value that we have computed at the previous iteration. Okay, and so this is again, so the challenger can accept this new play, or he can reject it and make a deviation. Okay, whenever it accepts, the game terminates. The value of the interaction is defined by the value of the play, the last play that was proposed. But what can happen also is that there is an infinite number of deviation by the challenger, and in that case, it's the value of the infinite path created by those infinite deviation, which is the new value assigned to the vertex. Okay, so we have shown that this the negotiation function is exactly equal to the value of the abstract negotiation games that I have sketched here. So it means that this value here is exactly the value computed by the abstract game that I have defined. Okay, so that's the first thing. So, I mean, this game is the important game to solve. And we have shown also that we can transform this abstract negotiation games so it's infinitely branching because player prover can choose any outcome, so it's an infinite path. We can transform it into a finite multi-mean pair of game with parity. So it's a multi-mean pair of parity game, and solving this multi-mean pair of parity game amounts to compute the value defined by the negotiation function. Okay, and so if you do, so this is for mean payoff, and for the parity objective, then what we get to compute this function is to solve a street game. Okay, so let's give you an example so that you can build intuition about this negotiation function. So I start with the worst case value as announced, no? And then I ask myself, is it possible for a player circle here to improve on the 2? Okay, and I claim that this is the case. Why? It's because if from 2, so first prover will say, no, you cannot obtain more, so I propose you A and C omega. And he can do that, right? Because A, C omega give 1 to player circle, which is consistent with the current annotation. But then player circle say, no, I'm not happy with this. I would like to deviate to B. But now comes the fact that in here, so player square should play rationally. Okay, and he cannot, so it means that prover now should give at least 2 to a player square. So he can no more go there and ask for player 2 to ask, so propose this path again, right? So he needs to propose something which gives at least 1 to player circle and 2 to player box, right? And you can see that the only play that will allow to get 1 for circle and 2 for box is to go there. Okay, and so he will go there, but no, what is the value that you get as player circle is 2. And so he can indeed improve the value that 1 against a square which is playing rationally. Okay, and so we know that this value is 2. Right, and then we can ask here, is it the case that the square can improve over the 2? Okay, so and then the prover will say no, you should go there, but then the challenger will say, no, I would like to deviate to this play, to this, because now I get 3, okay, and so hopefully maybe I will be able to repeat this. And then the prover say, okay, now from A, I need to satisfy the fact that player circle should get 2, so he will propose to go that direction, but then player square will propose to deviate again, and at the end of the day, he will get 3, right? Because whenever we are here, prover, the only way he has to satisfy 2, is to propose to go there, but then player square will deviate each time and get this row, and so you see that we will end up doing this cycle here, and so the value is now 3. And so the question now is, when should we stop this computation? So we should iterate this up to a fixed point, okay? And so it is guaranteed that there exists a least fixed point for this function. And this least fixed point, we can prove that it characterizes exactly all the SPE in the game. Okay, so now let's continue to consider this example, because it's quite interesting. So now we are F3 and then 2. And so now if we start, say, here and ask, is it possible to improve on the 2? You will see that prover now is in a very bad situation, because he cannot propose any path that would give a value 3 to player, so that would give value 2 to player circle and value 3 to player square, right? Because so starting from here, if we want to give 2 at least to player circle, we need to go there, right? But if we go there, we will not give 3 to player 2. And the only way to give 3 to player 2 is to cycle here, but then we give 0 to player 1. Okay, so it means that here, now instead of having 2, what we get is plus infinity. And this reflects the fact that in this simple mean payoff game, there is no SPE. Okay, so that's an example that was known for this before. But we can prove that by computing the negotiation function on this one, that it does not have any SPE. So because now there is no path, obviously, in the mean payoff game that would assign plus infinity to the players. Okay, so that's the result that we have. So for any prefix independent, so including objectives including mean payoff and parity, so the least fixed point of the negotiation function will characterize exactly the infinite path in the game that are supported by SPE. So for parity games, it's not difficult to see that this fixed point will be reached after at most V steps, right? Because in the case of parity game, it's a 0-1 information, and so this value will only increase along the application of the negotiation function. So it can increase only V times, V being the number of vertices in the game graph. For mean payoff game, unfortunately, we have examples where we will need an infinite number of iterations to reach in the limit the value of the negotiation function. But it turns out that so by studying the least fixed point of the function, so we can show that it's linear. It's partly linear. I mean, it's linear par morceau. So piecewise linear, yes. And so by knowing this, we can show that the complexity of the values that are assigned by the function are bounded because of the solution of the linear programs that are underlying the characterization of the least fixed point. And so we can guess it. And so this leads to an NP algorithm. And so for both of the objective, we can show that the problem is, so for example, the constraint existent problem for parity games is NP complete. Okay, and so remember that we need to solve street games to compute the negotiation function. So that's why you can do better than I mean, that's why you have an algorithm which is in NP. And yeah, we can prove hardness for NP using some not too difficult reduction. So we can also consider the problem of deciding if the given lambda is this fixed point. So this is PH2 complete. And we can also, because as I said, when we have computed this lambda function, we can consider a street automaton that characterize exactly all the SPE that are supported, all the paths that are supported by an SPE. And so we can, for example, verify in P-space that all those paths satisfy a given LTL formula. Okay, so that's, and for mean payoff, so we have shown that this is also an NP-complete problem. So if I give you two bounds for two vectors of value, answering the question, does there exist an SPE which lies between those two bounds, is an NP-complete problem. And in fact, in this case, as we have shown in the example, so it is also not, I mean, so we can also ask the plain existence problem, because there are some mean pair of games that do not have SPE. And so this problem of answering the question, does there exist an SPE in a mean pair of game? This is also an NP-complete problem. Okay. And so in that case, the notion of witness is non-trivial. As I said, I mean, we cannot easily guess showing that we can guess the fixed point is a non-trivial property. Okay, so I hope that I have convinced you that SPE are a natural solution concept for games played in sequence, because you have this problem of non-credible threats when you consider simpler Nash equilibria. So the fact that this solution concept is less studied, I think it's related to the fact that it's much more difficult to handle algorithmically. I mean, at least not from a complexity point of view, but from a conceptual point of view. I mean, the existence problem, for example, for mean pair of game was open, and so we were working on it for several years. And so it's only when we found this notion of negotiation that we had the good ideas to solve this problem. So in both cases, so we can compute effective representation of the set of outcomes of a game that are supported by an SPE, so either multi-mean pair of automata or street automata. And this allows us to answer the verification and synthesis questions that are interesting in that context.
I'm still a little puzzled that you kind of went directly to focus on outcomes. I would have taken the approach with the first characterize the equilibria. And if you have a characterization of equilibria, that would induce a characterization of outcomes. And so characterize equilibria, I would probably do it in terms of thinking about maybe three automata and things like that. Once I have a three automaton that characterize equilibria, I can derive the branches, which are the outcomes.
I mean, that's a viable path for parity. I mean, clearly, if you look at, I mean, maybe
also for any game, it's the strategy is a tree.
No, sure, but you have the I would say all the algorithm that comes with tree automata. That I mean, I do agree that characterization defining SPE you should start by
mean pair of tree automata. You could define a new thing.
Yeah, okay, but so my claim is that so you have the machinery to do it for parity game.
Yeah,
I'm quite sure that, I mean, this was done, by the way, by Hummels. I mean, I should maybe have mentioned that Hummels in 2007 has shown that by using alternating parity tree automata, you can recognize all the tuples of strategies that are supporting SPE.
SPE.
But so this leads to an X-time procedure for checking constraint problem. And so we wanted to somehow, I mean, come with algorithm based on other IDs so that we can, because, and then he proved in that paper that it was NP-hard. And so he left this gap open. And so for closing the gap, I mean, I don't think you, I mean,
you had to go deeper.
Yeah, or you have to go deeper on the particular parity alternating automata that you are considering. But here it gives, I think, a very elegant way of, I mean, with this value for parity, it would be 0, 1, right? And then basically you solve parity or street games at each iteration to change the values. And then, I mean, it's easier to, I mean, the outcomes are simpler object, right? They are traces, right? So and also it leads now to, I mean, once you have the automaton, the trace automaton that recognize every outcome supported by an SPE, then you can also naturally answer all the questions that I've mentioned as motivation in the beginning, right? Like those questions. So, I mean, but I agree. I mean, and I should have mentioned that, but I mean, this was a starting point from us. I mean, there was this Hummel paper, which was leaving this gap open. And so the question was how to improve this. And there was the mean payoff objective where even the existence was not known to be decidable. So, and then there I doubt that you can easily use, I mean, tree automata, because as you said, I mean, or you need to study tree automata with mean payoff objective. And
So, okay. Other questions?
So first, if for the mean payoff setting, do Nash equilibrium always exist?
Yes, because I mean, it's not trivial, but indeed, I mean, you compute this worst case value, and then you can prove that you can always build one path, at least that will be consistent with those worst case value.
Then I guess I'm kind of curious about the case where, you know, a Nash equilibrium would always exist in every subgame, but then there's no subgame perfect equilibrium.
I mean, we need to maybe put the quantifier exactly at the right place, but I don't know if what. So you say, is it okay? So I mean, for sure. I mean, here, if I take the subgame, there will be a Nash equilibria. So this is one case, right? I mean, this example. So it's an example where there is one Nash equilibria in each subgame, but there is no general subgame perfect equilibria.
I guess then to finish that off, then.
No, but it's because if you look at Nash equilibria individually in the subgames, so you do not use those, I mean, Nash equilibria to determine the value of the parent games, right?
Right.
So it's exactly what the negotiation function does here, right? So you first compute the Nash equilibria for each state. I mean, the values that characterize the Nash equilibria for each state. And then you ask yourself, okay, can I improve on that value if my adversaries are not willing to give up their worst case value? And then in this case, this is true, right? Because we see that when we are playing against an adversary here square that do not want to give up the 2, then he cannot beat us as before. So
that makes sense. But I guess my question then is, why is subgame perfect equilibria more corresponding to conceptually rationality when one solution concept exists and one is not guaranteed to exist?
I mean, that's a good question. I mean, if you don't have SPE in your game, maybe you want to consider Nash equilibria. But as I show in this example, I mean, the Nash equilibria here is not relevant. in my opinion, in the sequential game, right? So
But
because
then what is the rational behavior in a game where a Nash equilibrium exists and a subgame perfect equilibrium does not exist? Is it just to say we can't do anything, even if we can do
yeah, I
something
think
like this?
that it's a strange sequential game then. Yes, I mean it's yes.
Let's stop it here. It sounds like a good topic for the afternoon. People cannot hear you. Even if it's a simple question, people need to hear you.
So what happens for concurrent games when you?
Okay, so for concurrent games, so Rupak is not here, but he has done a paper that shows that there is not always Nash equilibria. I mean, this is quite easy because if you take, say, concurrent games and reachability objective, so you have games where you have a state which is limit sure winning, but not almost sure winning. So it means that, so from some state, you do not have a strategy to reach with probability 1, but for any epsilon, you have a strategy that reach the target with probability larger than 1 minus epsilon. And so there, basically, you do not have optimal strategies, then you don't have any Nash equilibria either. So you see? So even for Nash equilibria, in concurrent games, they do not always exist.
But we are happy with the situation that SPE doesn't exist, so maybe you can.
I don't. So you ask me if
No, he
there
didn't say he was happy.
Yeah.
He didn't say he was
I
happy.
just answer technically the question. So there is not always Nash equilibria in games. Okay, so I'm more interested in synthesis. So we have, further works where we are considering the synthesis of strategies that induce that all the Nash equilibria have some good property. Okay, it's rational synthesis, right? And so now we are trying to solve this also for SPE. But because, for example, SPEs in MinPerf are not guaranteed to exist, I would require that your strategy should allow the environment to play rationally. So you should not only, construct a strategy such that for all SPE it behaves well. You need to ensure that the set of SPE is not empty. Okay, so but that's part of the synthesis problem then. The definitions are what they are. There are games that do not have Nash equilibria, that do not have SPE. But when you are doing something more like synthesis, then you may ask your procedure to only produce good solutions that implies that the environment has some rational way to behave. And for all the rational behavior, your property of interest is enforced.
Okay, we'll stop here because we have the break. I just want to comment that I feel a bit a sense of cognitive dissonance here debating what is rationality and then opening the news in the morning. Thank you.
Yeah.